Having dealt with inelastic collisions, our next topic is, logically enough, elastic collisions. Remember that an elastic collision is one in which both the momentum and the mechanical energy are conserved, specifically the kinetic energy. So before we have one thing coming in, then they hit, and then two things go out. Keep in mind that although we drew it like this, it's entirely possible, it's entirely possible that in fact the thing will move out the other way, in which case we would have to treat the velocity as negative. Or when we grind out our numbers, if we got a negative velocity, that would indicate that it had bounced back the other way rather than moving forward. These two things give us two conditions, momentum and energy conservation. So if you imagine that we know the initial masses, which is pretty traditional, so we know M1 and M2, and we know the inbound velocities, i.e., that is, we know the inbound velocity here. And we're going to assume for our purposes in this class that the second object is at rest. That isn't strictly necessary, of course, but we'll see in a bit that that makes life a lot easier. So we're just going to focus on those. And so if we look here and we say, well, what is unknown? If all the things that I highlighted are known, what things are unknown? Well, we have the outbound velocity of object 1, and the outbound velocity of object 2. Why do I go through that rigmarole? Because we see that we have 1, 2 unknowns, and we have 1, 2 equations. So we would expect that we could solve this to get those unknowns entirely. That if we knew all the other things, i.e. the inbound mass and the inbound velocities, that we'd be able to solve exactly for the outgoing velocities. This system is in fact solvable, the system of equations, but the algebra is not at all pretty. I might write up a treatment just so you can see it. It's just some grungy, it really is just grungy algebra. It's not particularly illuminative or anything. If you do it, you get these following results, which are basically starting points for us. That the outbound object number 1, so again, to draw our picture, we have this thing coming in with V1 xi, and then after the collision, it's leaving with V1 xf, but there was also object 1 or object 2 here at rest, and then kerpow, something happens, and then object 2 is skittering off, V2 xf. And we can get exact formulas for those two velocities, the outbound velocity for 1 and the outbound velocity for 2. I'm going to have this on the next couple of screens so you can use it. Eventually, you might want to commit it to memory. The AP1 committee doesn't tend to expect you to know these formulas, but knowing them isn't a bad thing. All right, a 1.2 kilogram hockey puck sliding at 6.7 meters per second collides elastically with a 2.2 kilogram puck at rest. How fast is the second puck going? So after the collision. So we go here, the second puck is this one, i.e. the 2. Not surprisingly. So we're going to take twice the original mass over the sum of the masses and multiply it by the inbound speed. And if you grind that, you get 4.73 meters per second. So it takes off slower than the original guy, but not crazy much slower, which makes sense because the masses are close. Next question asks how fast the original puck is going. That would be this one. So we say V1x final is the difference in masses, 1.2 kilograms minus 2.2 kilograms, over their sum, 1.2 plus 2.2, times the speed of the inbound guy, 6.7 meters per second, and we get minus 1.97 meters per second. We want to kind of take at least a little look at this minus sign. What does the minus sign tell us? Well, it tells us that it bounced back. So if I were to draw these things as a picture, I would have this one heading into this thing that is at rest, and then stuff happens. And the first one is now moving this way, and the second one is moving that way, actually even faster. A 1.2 kilogram hockey puck is sliding at 6.7 meters per second and collides elastically with an identical puck at rest. How fast is the second puck moving after the collision? So again, we're going to use this one. And we're going to say V2xF is twice the original mass over the sum of the masses times the original speed. Hey, but wait a minute. If we look at this, we see twice the original mass over the sum of the masses is going to be identically just 1, because this is 2 times 1.12. That's always going to be true if the masses are identical. And so we end up with just 6.67 meters per second. So something comes in at some amount, hitting something at rest. The thing at rest takes off with the same amount. Oh, but wait, for momentum to conserve then, since these have identical masses, it has to be that this one comes at rest. That's the only way to get the momentum to work out. If m times v here, right, m1 times v is m2 times v. So if these two have the same momentum, then these two have the same momentum. If you check it, if we go back up here, we say, oh, wait a minute, if we had gone back to this equation, to this one, we'd have seen that we have 1.2 kilograms minus 1.2 kilograms, so this is going to be identically 0. And this is kind of an interesting and important side case, which we got here obliquely, but you really want to commit to memory. Identically massed objects, if one of them collides elastically with the other, and the second one had been at rest, then what happens is the second one takes off with the original speed, and the first one stops. You see this in games of pool all the time. Your textbook says whenever a cue ball hits another ball, that's not true. But when two numbered balls hit, you will often see this happen, unless there's some weird spin on it, where they will hit and one will stop and the other will take off with its velocity. All right. A 10,000 kilogram truck moving at plus 5 meters per second collides elastically with a 0.15 kilogram superball, which we assume at the moment is, say, hanging there in space somehow. What is the truck's velocity after the collision? Well, the truck is the original guy, so we would use this, and we would say V1xF is 10 to the 4 minus 0.15 over 10 to the 4 plus 0.15 with kilograms. So kilograms, so I'm not going to write it, times 5 meters per second. And you can throw it into a calculator, or you can just see this is just going to be 5 meters per second, because these numbers don't change these numbers by enough. That this is smaller by a little bit and bigger by a little bit, but it turns out to be number 1. Throw it into the calculator and you'll get 4.9997 something, which to our sig figs is definitely 5 meters per second. In other words, not surprisingly, the truck doesn't even notice that it hit this thing. It might slow down nominally because it's 4.9999 or whatever, but really it just drives through. Same setup. What is the ball's velocity after the collision? So we want this guy. So here we say V2xF is twice the truck's mass over the truck's mass plus the ball's mass times the 5 meters per second. And we can see that basically if you run this in a calculator, you're going to get 9.9993, I think. You get 10, definitely, to within our sig figs. And that's not too surprising because this factor is essentially irrelevant. Right? Essentially irrelevant. And so we have 2 times 10 to the 4 over 10 to the 4, or just 2. And so what we find out here is that in the case of a big object hitting some little lightweight object, the big object moves through with the same speed, and the little object takes off with twice the speed when stuff happens in here. And that's also kind of a useful thing to know. that the big object plows through and the little object takes off at twice the velocity. Change of pace, these are the kind of questions they seem to love on these tests. They say a puck of mass 1.5 kilogram, which is shown in blue, collides with a puck of mass 3 kilograms, slide is shown in red. Their velocities before, during, and after the collision are shown. What type of collision is this? So we look here and we say, well, I've got that it started with speed 6 versus speed minus 2, or velocity minus 2. Stuff happens in what we can probably just call the collision time, which is clearly something like this time. And as usual, we don't really care what happens in that time. We can just take the momentum before and after and take the kinetic energy before and after. We should probably confirm that the momentum works, although I guess we can check it quickly. So let's try the momentum first. We have 1.5 kilograms times 6 meters per second plus 3 kilograms times minus 2 meters per second equals an initial momentum of 3 kilogram meters per second. That's the before. After, we have 1.5 kilograms times, now that's our speed, which is minus 2 meters per second. And we add 3 kilograms times its new velocity, which is plus 2 meters per second. And those numbers come out to be, also 3 kilogram meters per second. So they weren't lying to us. This is an actual collision process. Now we can classify what type of collision it is. That's a little more annoying, but what we have to do is take the same velocities, but now compute the kinetic energies. And in the interest of time, that's done down here. And we find that the initial kinetic energy was 21 joules, but the final kinetic energy is only 3 joules, and therefore we are definitely in the case of an inelastic collision, because that's the case where kinetic energy is not conserved, but the objects haven't stuck together. All right, a puck of mass 2.25 kilograms, shown in blue, collides with a puck of mass 4.5 kilograms, shown in red. Their velocities before, during, and after the collision are shown. What type of collision is this? So we look over here, and we could do the same thing. We could check the momenta, but we'll take their faith on it. We should note that the collision time is something like, this very short collision time, which is fine. But then before we go any further than that, we notice that after they have essentially the same speed, where they're bobbling back and forth around 1. This is an experiment of some sort, maybe, so that's why they're uneven. Honestly, they're drawn like that just to show that they have the same speed, and I didn't want one symbol to overlap the other. But we know that when two things come together and then move off at the same speed, that's a perfectly elastic collision. So it's type A. All right, a puck of mass 5 kilograms, shown in blue, collides with a puck of mass 2 kilograms, shown in red. Their velocities before, during, and after the collision are shown. What type of collision is this? There really isn't much we can do other than grind out the kinetic energies, so that's what we'll do. I'll do it on the next screen. When we grind out these kinetic energies, we find that the first one has 122.5, and after collision is also 122.5, so this is a perfectly elastic collision. One of the things I haven't shown here, but they could easily do for you, although the formulas we only do the formulas for when they're at rest, they easily could have had these two things at different speeds at the start. So you still have to check it. You're not guaranteed anything by the fact that this starts at rest, and the fact that it doesn't start at rest doesn't guarantee that it isn't perfectly elastic. You really do have to check before and after for both kinetic energies.